thank you for the invitation to give a class here at this university. Pleased to be here and honored to give this class in discrete choice modeling. As Dr. Chu was saying, I'm Italian. I did my PhD in Italy. This is quite an unusual track for being a faculty in the US. Usually, you are in the US if you have a PhD from the US. So I did my PhD in a very remote place in Italy, and then a postdoc in Belgium. I worked for applied mathematician in Belgium, and I was given a fellowship from the European Commission. So just to let you know, the European Commission also found young researcher from abroad if they want to have a research experience in Europe. There are dedicated fellowship for that. So it's not just about the US, but also Europe is open to a new class of researchers. And after that, I received an offer to join the faculty at the University of Maryland. At the time, Professor Hani Mamasani was there. I believe all of you know Professor Mamasani. Now, my expertise, I've worked all my life in discrete choice modeling. Actually, in the US, I teach three or four classes in discrete choice modeling. So the first class is the basic discrete choice modeling. It's mainly from the book Ben Akiva Lerman. And the second class I teach is on advanced discrete choice modeling, which will be mainly what I'm going to teach here. And this is where I teach a class of advanced modeling, discrete choice modeling. So all we are doing in research now. I don't know how much you know about discrete choice modeling, but in the last 10 years, discrete choice modeling have changed a lot for a number of reasons. Mainly because our computational skills have improved, and we can afford to estimate models that was impossible to estimate 20 years ago or 30 years ago when McFadden was working on Logit. So what we can do with discrete choice modeling is much more advanced with respect to what we were doing, say, 10, 15 years ago. I was also told, so if this is the program, so I'm going to give an overview today of discrete choice modeling, and I'm trying to communicate why advanced discrete choice models are needed, and in which way we are using this advanced discrete choice modeling. So I want you to know why we need discrete choice modeling, advanced discrete choice modeling, and when. Because it's nice to use this advanced method, but it's also good to know when you need to apply this advanced method. After that, tomorrow I'm going to talk about nested logit, generalized extreme value models, and probit models, which are kind of advanced and have been used, but now, for example, there are many new researchers who are using again probit models, including me, because all the simulation methods that we have developed are adapted for probit models. And I believe you all have heard about mixed logit. So I've been working for the last 10 years on mixed logit model. And these were introduced by Ken Train and McFadden, and they have a book on that. And actually, many researchers all over the world are working on mixed logit. Many of the publications in discrete choice modelings now are based on mixed logit. So I've divided this in two parts. This is more about the way you use mixed logit, and in particular the two specifications, random coefficient specification and error component specification. So this is how you use mixed logit and why you use mixed logit. And this is more about the estimation. These are models that are difficult to estimate and that can be solved because now we know a lot about simulation. So, and in fact, the book is called Discrete Choice Analysis with Simulation. So this is very important. So on Friday, I'm going to introduce another class of discrete choice models, which this time is about joint decision about discrete and continuous models. So we are now working on integrated several choices, and we are not just working with discrete choice, but also with continuous choices. So this means, for example, that we are able to deal jointly with decisions that concern discrete decisions, like, for example, which kind of activity I'm going to undertake. For example, today, after this class, I'm going to go out to the restaurants, or I'm going to study in my room because I needed to prepare a class, and how much time I'm going to spend on that activity, right? So this is the continuous decision. So these new models are able to deal with both discrete and continuous decision. In particular, this is the method developed by Professor Chandra Bhatt. So Chandra Bhatt is the professor who is publishing extensively on these advanced discrete choice models. And also I'm going to talk about continuous probit. That is what we are doing at University of Maryland. And actually, this is the PhD dissertation of a student of mine. She's Chinese. She originally was from Tongji, and with a Canadian student of mine. So we are working on this continuous probit. And in particular, we are applying this continuous probit on the decision concerning car ownership and use. So this is a typical discrete continuous decision, because you need to decide how many cars an household hold. For example, 0 car or 1 car or 2 cars. I don't know about the situation here, how many cars per household in general, and which type of car. For example, I'm going to have a small car, a large car, an SUV, a truck. Or for example, how old is this car? I'm going to buy a new car or a second-hand car, and so on. And the continuous decision is how many miles I travel with that car. And we can jointly estimate this model with this continuous probit that you will see here. So this is really the day about my current research, and I've also introduced recently another kind of discrete choice modeling that is called dynamic discrete choice modeling. And in particular, when we estimate discrete choice models, we estimate choices, but we don't know when these choices happens in times. We know that these choices happens, but in particular, we don't know when these choices happens in time. Let's see if I'm... No? Yes. We don't know when these choices happens in time, and so we are studying, we are introducing these dynamic discrete choice models in order to be able to understand when choice happens in times. For example, we are working on, again, on car ownership, and for example, we want to know when people are going to adopt new cars. For example, suppose that you want to buy a car and you expect major innovation in technology over time. For example, in the US market, we are expecting the car industry to deliver new models of car. So the decision in that respect is, am I going to wait for the new car to come, or to buy now? And so my decision is a kind of optimal decision in time, in which I decide, well, I stay with my car because I have expectation about the future. I expect a new product coming into the market, so I'm going to wait for the new car. All right, so this is mainly about discrete choice models. As you see, there is a lot to say. I was also asked by Dr. Chu and Dr. Cheng at the University of Maryland to illustrate data and data collection. So I'm going to have 2 classes. One is on National Household Travel Survey. I'm not sure if you have a National Household Travel Survey running here in Taiwan. Do you collect data? Okay, so it's the same situation in China. So last year I made a presentation at China DOT, and they were very much interested in knowing how to collect data for transportation planning. So which kind of data you need in order to estimate these models. So these models are very nice, but you need data in order to estimate them. And you need data collected on a regular basis. It's not that you collect the data 1 year and then you forget about this data. So in Europe and in the US, we have developed a technique to collect behavioral data. And this is the main sources of data for all my models. In particular, this National Household Travel Survey in the US, which is called NHTS, they collect behavioral data every 6-7 years. Last time they collected data was in 2009, so we are working with that data. So they collected data, for example, in 2001 and then 2009. So there were 8 years between the two. And these questionnaires are quite standardized in the sense that the way National Household Travel Survey are collected in the US is very similar to the way that National Household Travel Survey are collected in Europe, for example. So in my opinion, it won't be very difficult to transfer these techniques, for example, to China or to Taiwan in order to collect behavioral data. Well, the problem is that we know how to collect them. Data that we collect are very reliable. It's a vast source of information about the way people travel. And actually, these are used to calibrate any 4-step models in the US and in Europe. But of course, they are very expensive. And also, you need a class of people trained in statistics and data collection and transportation. So you need a lot of multidisciplinary information in order to be able to have National Household Travel Survey collected. So, but this is not impossible. When I was in Belgium, actually, we collected the first Belgian household travel survey. So Belgium was in the situation of Taiwan 10 years ago, until we convinced the Ministry of Transport that this was needed, and then we collected a National Household Travel Survey. It was very successful, and now they are collecting this kind of data every 10 years. So they had one in 1999, and they had another one in 2009. So this is feasible, and this is you, the young generation, who will be called to give this suggestion to the Ministry of Transport. And I should say that many of my models now are based on the National Household Travel Survey. You will see some of this application when I will be talking about this. Now, I will also talk about revealed and stated preference method, and this is more from my experience in Europe. So revealed and stated preference methods are very much used in Europe for a number of policy analysis. And we have developed a discrete choice modeling technique in order to analyze jointly revealed and stated preference method. There are also a lot of publications on revealed and stated preference method. These are now also used in practice. It means that for project, it's not just research, but for real project, we use stated preference method. So what is the difference between, for example, this and stated preference is that this is real behavior, right? We ask people, what did you do, for example, on that day? Where did you go? Which was the mode of transportation? Why? And so on. So this is real behavior. Stated preference is about hypothetical behavior. We ask people, what are you going to do in the case these scenarios are presented to you, and are used on all kinds of projects. For example, in the Netherlands and in the UK, stated preference methods are used a lot to evaluate value of time. And value of time is a very important measure. I will define value of time later. Value of time is a very important measure for all kinds of benefit cost analysis, right? It's the magic number that you put in the benefit cost analysis in order to see, for example, if building an infrastructure is worth or not, right? I've been using stated preference method for example, to evaluate willingness to pay on HOT lanes, high occupancy toll lane, or high occupancy vehicle lanes. It's where you drive with many passengers in the cars in order to avoid to pay toll, or you are alone in your car and you pay a toll in order to use a special lane in which there is less congestion. I don't know if you have HOT, HOV lane here in Taiwan. Okay, so in the US we are talking about this. There are some implementation, but not many. For example, I've done a study for the Beltway around Washington. So this is, I think I'm going to conclude with showing you how to estimate in real life these models, and in particular, I'm going to show you the estimation of this model with Biogym. Biogym is the software, this open source, many researchers are using Biogym. And so I will show you how to use data and software in order to have these models estimated. However, I'm talking especially to the students. What we have learned in the last 10 years is that using software, existing software is not enough anymore, in the sense that, well, you can use existing software to run models, but if you want to develop your own models, you need to develop your own software. And this is actually one of the main difficulties I have with my students, because they are not well trained in programming. This demand modeling is becoming a multidisciplinary discipline. You need knowledge from statistics, transportation, optimization, and also you need programming skills, very advanced programming skill. So that's an advice for the students, and so this is how I'm going to close these 8 days of classes. So the way I've organized today is I'm going to give you a broad, very comprehensive overview of multinomial logit and of the basic discrete choice analysis. I think this was necessary because I want you to see the difference between the old way of estimating discrete choice analysis and why we are applying advanced discrete choice analysis, right? So I've structured this in order to give you an idea of what we are doing now that it was impossible to do before with the classic multinomial logit. And in particular, so these are the main 3 limitations that we can handle now with advanced discrete choice modeling. In particular, I'm going to talk a lot about taste variation, substitution pattern, and repeated choice over time. So taste variation is that everybody here has a different sensibility to different things. For example, with respect to travel time. So travel time for me, the weight that I'm giving to travel time is different from what Professor Chu is giving to travel time, and so on. So each of us has a different taste. And you cannot handle this with classical multinomial logit, or you can do it, but with limitation. Substitution pattern is the classical IIA property of multinomial logit, so the independence from irrelevant alternatives, which is a property of logit. We know it's a limitation. Sometimes it is a desirable property of logit, but we'll see that with this new model, we can overcome this limitation. And the third one is repeated choices over time, or panel data. So we have more and more panel data available. Panel data means that you collect data over time, or you have repeated observation from the same person. In the effort to connect always this with data, for example, what panel data is now very popular among the activity-based community, because they want to know travel behavior across a longer period of time. So you can collect travel diaries, so everything about travel behavior over a week, for example. So we are asking people to describe how they are traveling over, for example, an entire week, because we want to know differences across Mondays, Tuesdays, Wednesdays, Thursdays, Fridays, and weekends, for example. So we ask people to describe their travel behavior over time. And so we collect repeated observation from the same person. And there is no way that you can account for this repeated effect with multinomial logit. So you need advanced method in order to account for repeated choices. Or, for example, stated preference is another example of repeated choices. What we do in stated preference is that we show different scenarios to people, and we show different of these scenarios, but the respondent is always the same. So usually we present scenarios to people and say, well, between these two scenarios, which one are you going to choose? The first time, the second time, the third time. Usually we present between 9 and 16 scenarios to each individual. It means that there is correlation amongst the responses given by the same respondents. And so the only way to handle this is advanced discrete choice modeling. Then I'm also going to present different ways to account for taste variation. For example, nonlinear representation of the utility, what is the consumer surplus, the derivative and elasticities, the estimation, how we judge if a model is good or not, goodness of fit, and some hypothesis testing. So let's start from logit models. So, well, a suggestion that I give to all my students: before you start to apply an advanced discrete choice models, for example, a mixed logit, first you need a good logit models estimated. So it's very nice to use advanced discrete choice models, for example, mixed logit, probit, and so on. But before, you need to understand well the data and the properties of the models with a very nice logit models. And there are a number of reasons for that. First of all, so the first reason is that when you estimate logit models, you have a closed form for the choice probabilities. So you can get the results instantaneously, right? It takes seconds to estimate a logit models. While if you want to apply a nested logit or a probit or a mixed logit, it will take you sometimes hours to get the results. So before you start any advanced discrete choice models, have the data cleaned and have a good logit models estimated. So the reason why also logit model is so popular is also because you have this closed form choice probabilities. So no need for simulation, right? So the hypothesis under which you can estimate the logit models gives you a nice closed form choice probability, and this is what made logit very popular at that time, because people were, McFadden was working on this because it was very difficult to estimate or to solve integrals, multidimensional integrals. Still it's difficult, it's possible, but still but it's possible. So that's why logit is so popular, and I would suggest you to start always from logit. So the hypothesis under which we estimate a discrete choice models is that we have decision makers, which are labeled N. So I have decision maker N. They face J alternatives. For now, we are working with discrete alternatives. It means that we have a number of discrete alternatives, a finite number of discrete alternatives. And we give to each person and to each alternative, we specify an utility, right? We have utility for individual N and alternative J. And this has two components, a systematic component, V and J, plus an error term. So the systematic component is everything we can measure and specify, right? So in V, we have all the characteristics that we can collect from a travel survey, for example. So this includes travel time, travel cost. For example, for public transportation, this can include frequency, number of changes, access to the station, egress time from the station, and so on. And also this includes social demographic characteristics. And this is very important. So for example, this can include gender, income, a number of cars in the household, and so on. So you have both level of service variables. Level of service variables are travel time, travel cost, frequency, and you have social demographic variables that are in V. And this is everything you can measure. And in particular, you can measure this from a survey like National Household Travel Survey or from stated preference data collection. And you have a random term, and this is everything it's not observed by, it's everything not observed. Right? Usually we are engineers and we think that we can measure everything, but there is always something that we cannot measure, and everything we cannot measure is in that epsilon, in that error. This error also includes error that you make on the V part, right? For example, remember that you needed to specify an utility for all individuals and all alternatives. Now, and this is a very difficult part because usually when you have, for example, data from the National Household Travel Survey, we ask people, what did you do yesterday, right? And the guy will say, well, yesterday I went to school and I used my bike and it took me 30 minutes, right? In order to estimate a mode choice model for one of you, you need to build the utility for all the alternatives in the choice set. It means that you need not only the utility for the bike, but you also need to specify a utility for the non-chosen mode, right? For example, there is a shuttle, there is a bus. You need travel time and travel cost on this bus. Now, you are not going to reveal me which is the travel time and travel cost on that bus because you have no idea. You have never taken it, so you have no idea. So it's the analyst, it's me, on my desk in the US, trying to guess what is the travel time and the travel cost on a shuttle here in Taiwan. And believe me, this happened all the time. For example, I've estimated the model for Sydney, Australia, without being even once there. So I was making all these assumptions. So it means that for non-chosen mode, when I estimate travel time and travel cost, for sure I'm making some, there are errors there. And so epsilon is accounting for not just non-observed random variables, but also is accounting for the errors on the specification of this V, right? All we don't know, or all as mistakes, is in this epsilon. Now, so this is the specification. So U is systematic components plus random term. And the hypothesis under which McFadden was able to solve this in a closed form, he said, well, let's say that epsilon is independently and identically distributed extreme value. And under this distribution is also called Gumbel type I extreme value. That's why GV, right? And this have density and cumulative distribution function that are this. So this is the Gumbel. And very important, we assume that the error has zero mean and variance, which is pi squared divided by 6. Zero mean is acceptable as long as you have a complete set of alternative specific constant in your V. Do you know what is an alternative specific constant? My choice set, the discrete choice set C, is in the example I was saying is bus. Then I have a bike, and I have car, right? So this is my C. So it's discrete. I have three alternatives. So on the base of this, I'm going to write the utility of N, bus, the utility of N for bike, and the utility of N for car. So alternative specific constant are dummy variables that are 1 for the alternative for which they are specified and 0 otherwise. So I set this as the base. I cannot estimate 3 alternative specific constants. So I set this. So I will have alternative specific constant of bike, and I'll have alternative specific constant for car, right? So as long as I have a complete set of alternative specific constants, so this is 1 for bike, 0 otherwise. This is 1 for car, 0 otherwise, and I've set this as a base. So as long as I have these 2 alternative specific constants, I can say that the mean of epsilon is 0, and that the variance of the distribution is pi squared divided by 6. And remember this because this is also the scale of the model. This, you will see this many times, and researchers in transportation, they forget that there is a scale of the model. So this is a very important factor. Remember also that although epsilon is extreme value I distributed, it's a gamble, the difference between 2 gamble is a logistic, and a logistics approximate a normal. So this is what it made this very successful. It was also because it was difficult to use normal. We will see that when we will see probit. But the difference between 2 gamble is logistics, and logistics approximate well a normal. And the other things you need to know is that in discrete choice models, all it matters is differences, its differences. What is going to give you the estimation is not the absolute value of the utility, but is difference across utilities, right? So it doesn't matter if, for example, the utility of bike for you is 10 or 10,000. What it matters is that the difference between the utility of bike and the utility of bus is a certain number, right? So that's why what it really matters here is the difference between the errors and the utilities, right? So if these are the errors for 2 alternatives, and if these are ID extreme value, then this is the difference, and so this is the choice probability, right? So this is the classical expression of binomial logit. So this is the difference between utilities, and this is the choice probability. Remember that one of the assumptions that we made in order to arrive to this closed form mathematical formulation is that the errors are independent from each other, right? So this error is independent from this error. And so this is what it makes the IIA properties for logit. So this property sometimes is good. Sometimes it's something that we don't want. It's not a desirable properties of logit. But sometimes it's a good property. Well, you can kind of overcome this difficulty by having a good specification of V. So in order that what remains are not correlated. So what I want to say here are 2 things. So it's nice to have these advanced discrete choice models, for example, that take into account very difficult correlation patterns. So you want all the alternatives correlated, right? And you can do that with nested logit, with probit, with mixed logit. But before you do that, make sure that your logit has a good specification of V, because sometimes you can kind of mitigate this IIA problem by having a good specification of V. That's why I'm saying, remember that the first things to do is a good logit before you go into a more advanced discrete choice models, right? Okay, now I also would like you to think about this IIA problem. So what is the IIA problem? Is that IIA problem in logit models is that the ratio between the probability of choice of two, so the probability of choosing bus divided the probability of choosing bike does not depend from the probability of choosing car. So this is the problem on IIA properties. So if you want to avoid this, you can, what you can do is use a different models that allows for correlated errors. And you can use, in that case, nested logit or probit or mixed logit. But before you do that, respecify the representative utility so that some source of correlation can be captured, and or just say, I'm using the logit model, but I know that this is an approximation, and I know that there is a problem there. So this is the derivation of classical discrete choice models. So you can write down the probability that n chooses high as the probability that epsilon nij is less than the difference in the utilities for all the alternatives. And you can then calculate this probability. This is the product over all the alternatives. And then you have the derivation of the logit model. So this is kind of the function that describes the probability with the way the probability as a function of the utility, of the systematic utility. Remember, these discrete choice models are non-linear models, right? So this is not like, it seems like linear regression, but it's not linear regression. So there are a number of things that are kind of similar, but the way that the shape of this probability, the fact that this probability is non-linear will make some differences the way you see the results of this. There are some nice properties here. The probability is between 0 and 1. It's what you want for a probability. The probability is never exactly 0 or 1. That's why we have a random utility model. The probability is never 0 or 1. So when V rises, the probability of choosing that alternative is going to be is rising to 1. When V and I decreases, the probability is going to 0, right? So when V decreases, the probability is going to 0. When V increases, the probability is going to 1. The main changes in probability of choosing an alternative happen here, right? When there is a 0.5 probability of choosing one alternative. So if a probability of choosing an alternative is very low or very high, doesn't matter what you change in the systematic component of the utility, it won't make much difference, right? So it means, in practical terms, it means that in the US, the probability of choosing public transportation is very low, right? It's about 5%. So it means that even if we make huge changes in travel time for the public transportation, it means that this probability are not going to change much. And this is exactly what we observe, right? For example, in European cities, the probability of choosing car versus public transportation is 50%. So we know that if we improve just the comfort of public transportation, we are going to attract many more passengers, right? So you see the interpretation of this. So you can see the nice mathematical properties of this, but also the interpretation that we have in transportation. That's what I like about this. everything is based on very good mathematical and statistics concept, but then you have interpretation. So try to do this every time you estimate a model, what the model is telling you, right? So it's nice to estimate the model, but then what are we doing with that model? Especially if you are working in a consulting firm, for the students, they want to see what you can do with that model.
I'm curious about the second approach to deal with the correlation among alternatives. Could you give an example?
Example?
Is it an usual way to use this approach to deal with the...
Well, it's yeah, I don't know if I can give you, because it depends on the problem. It means that you need to re-specify the V part and include other variables that can account for the fact that there is correlation. For example, I don't know, but for example, suppose that in your model you have car as a driver and car as a passenger, right? So these two alternatives are very likely to be correlated, right? So, and you want, for example, to introduce a nest there, estimated a nested logit, saying that, so you have car as a driver, right? And car as passengers. Now, these two are cars alternatives and are very likely to be correlated. So instead of having a logit, suppose that you have a nested logit here, and then you have, for example, this with public transportation, right? Now, for example, you can improve the specification of this in order to, for example, take into account that, so for example, here you can introduce size of the party. For example, you can say that here there are 2 people, or 3 people, or 4 people, and this is kind of accounting for the fact that there are multiple people in that car, and so you are improving the specification. So you can add more variables like this, and hopefully this, well, there is no guarantee that this will solve the correlation issue, but it's about improving the specification. All right?
So should we test it?
Yeah, you should test this, and there is a test for IIA properties before you go ahead. I would like now, I do a lot more in Maryland when I teach this, but given that here I have a limited time, so let's see how we specify in reality these utilities, right? What we put into these utilities in order to specify these models. Now, I don't have a transportation example here, but this is also good. I think here it's also a management school, right? So this choice model is not just applied in transportation, but it's also applied in many other disciplines. And for example, now what is very popular is to evaluate energy choices, or in revenue management. There are people in OR working a lot with these 2 choice models because they understand that this is a very important mechanism to understand how people make choices over different products, right? So it's used in marketing, in energy studies, in revenue management, in health studies, and so on. So this was about household choice between a gas and electric heating system. So you are a household and you need to decide which heating system you want for your own house. And you have the choice between gas and electric, and this is quite a common problem in the US. So either we heat our house with gas or electric system. So then we have 2 alternatives, right? Our problem has 2 alternatives. You have the utility of a gas heating system and the utility of an electric heating system, right? So you need to specify the utility for each of the alternatives. And the V here is the price, purchasing price, and the operating cost. So there is a trade-off between what you pay upfront in order to have your heating system and what you pay every month on your bill in order to use the system. So if we are under the hypothesis of logit models, the epsilon of G and epsilon of E are IID extreme value distributed. The probability of choosing the gas system is the exponential of the utility of the gas systems divided by the exponential of the utility of the gas system plus the exponential of the utility of the electric system, right? Now, so what you are doing here, so you use your data and you estimate beta 1 and beta 2, right? So at the end of the day, what we do, especially when we apply discrete choice models, is estimating this coefficient. So what you do is specify the utility, estimate the model on your data set, and get B1 and B2, assuming that you have some hypothesis on the epsilon, for example, that these are IID distributed. Now, there are a number of important information that you can derive from the estimation of a discrete choice model. The first one is the ratio between the coefficient, which is, for example, in this case, beta 2 divided by beta 1 represents the household willingness to pay for operating cost reduction. So the idea is that I'm willing to pay in order to pay less on my monthly bill, right? So I'm willing to pay for a more expensive system, but I want to save something on my bill. And so this ratio is exactly what I'm willing to pay in order to save on my bill every month. Now, if that was an example from transportation, what we estimate is value of time. As I said, this is very common. Value of time is the beta time divided the beta cost. So this is beta time divided beta cost is how much I'm willing to pay in order to save a unit of time, of travel time. So for example, if I'm telling you that by using the high-speed train, you can save 10 minutes, is how much I can charge you in order to save these 10 minutes. That's the way it works for high speed, right? So you save your time and you are willing to pay more. So for example, in Italy, they have introduced the high-speed rail, and there is a difference between the normal train and the high speed. For example, from my city, Naples, to Rome, the normal train takes 2 hours and costs about 15 euros. And if you take the high-speed train, this is 1 hour and you pay 40 euros. But I think they made a mistake because they consider that people, in order to save 1 hour, were willing to pay 25 euros more, which is a very high value of time. So the result was that trains were empty, right? So this is how we use this. So you need to estimate this in order, for example, to set the price of the ticket. And this is also one of the applications that people, as I said, in revenue management are doing, because they are calculating exactly how much you are willing to pay in order to buy a ticket, for example, an airplane ticket or a high-speed train ticket. And all these studies are based on this, on value of time. And the value of time, as I said, is derived from this kind of. So if you make this calculation, for example, suppose that out of your estimation, that's what you get from the models, right? Out of your estimation, beta 1 is minus 0.2 and beta 2 is minus 1.14. Then you calculate this ratio and you get that you are willing to pay $5.7 for a system whose annual operating cost is $1 less. So this is the interpretation of the willingness to pay from choice models. So this is exactly, so now that you have, this is the first hour, so I kind of gave you an overview of discrete choice models, how we estimate them, and the lesson that we learned from discrete choice models. Now, any question? Because now I'm going to illustrate the power and the limitation of Logit. And the purpose of this is to let you understand why you need these advanced discrete choice models. So as I was saying, The interest of estimating advanced discrete choice models is to overcome these three limitations of logic. So taste variation, substitution patterns, and repeated choice over time. However, remember that when you apply logic models, you can kind of estimate taste variation, but it's a particular way of estimating taste variation. And this is what we call deterministic taste variation. So what is a deterministic taste variation? So it means that you can estimate this taste variability across individuals by taking into account the social demographic characteristic of the individuals. For example, a classical application in transportation, for example, value of time, right? When you estimate value of time this way, it means that all the population has one beta time and all the population has one beta cost, right? It's like I'm estimating value of time here, and I'm estimating that beta time, for example, is 0.01. Right? So I say for this class, beta time is 0.01, right? And this is estimating travel time as a generic variable. There is no taste heterogeneity here, right? I'm assuming that all of you have the same taste for travel time. Now, I understand that here there are graduate students, there are researchers, and there are professors, right? All of you, these three categories of people have different income. And so they have and I suppose that they have a different perception of travel time. So what I can do is I estimate a beta time for graduate students. I estimate a beta time for researchers. And I estimate a beta time for faculty members. Right? So it means that I'm interacting travel time with social demographic variables that in this case is the status, right? Being a graduate student is a status. Being a researcher is another status. Being a professor is another status. And in particular, I'm using the status here as a proxy for income in reality, right? Different income will produce different taste versus travel time. And so, once I've done this, it means that I'm taking into account taste heterogeneity, but it's a deterministic taste heterogeneity because it's determined on the base of the characteristic of the decision maker. And I can do that with different variables. I can do that with status, with gender, with income, with car ownership, and so on. These are the variables. Or for example, I can do this by purpose. Usually when in a four-step model, you know what is a four-step model, right? So it's the classical framework for transportation model system. For example, mode choice is estimated on purposes. So, and the classical four purposes used is work, so commute, which goes with education, shopping, leisure, and other. And you have value of time estimated with these four purposes, and this is another way to account for deterministic taste variation. Now, and you can do this with logit. That's why I was saying, before you start going into a mixed logit, for example, estimate a good logit model first. What logit cannot do is to estimate random taste variation. What is random taste variation? It's like of fitting a curve across you guys. So I'm going to give to each of you a different value of time. And this distribution is going to be, for example, a normal, a log normal, or a non-parametric distribution. So instead of having 3 values, I will have, I don't know how many we are here, I'm going to have 40 values of beta that are drawn from a random variable. So beta is not going to assume just 3 values, but beta is a normal with a mean mu and a standard deviation sigma. So I'm fitting a curve on you, and I'm going to extract 40 values, one for each of you, randomly from this distribution. So if you want beta to be a random distribution, you cannot do this in logit. You need to do this with mixed logit. Or if this is a normal, you can do this with probit, right? So we will see this. So logit is good for taste variation, but just deterministic taste variation. If you want random taste variation, you cannot do this with logit. You need a more advanced method that is either probit for normal or mixed logit that is more flexible with the distribution. You can have different distribution from normal. Okay, so this is the first difference between classical multinomial logit and advanced form of discrete choice modeling. Implies proportional distribution across alternatives. So this is the infamous IIA properties. So remember that logit suffers from these properties, IIA properties, independent from irrelevant alternatives. It means that the ratio between the probability of choosing two alternatives is not dependent from the presence of a third or fourth alternatives. And usually this is a problem, but not always a problem. In some cases, it's a good property, and I will show you when this is a good property. And so in the case you don't want this, you need to use advanced form of discrete choice modeling, and in particular, you can use nested logit. You can use, again, probit, or you can use mixed logit. So this is the second property. The third cannot capture the dynamic of repeated choices. So let's explain this a little bit better. All right, so I was describing these repeated choices, and I said repeated choices are from, for example, panel data, or from stated preference method. Suppose that I'm doing a panel data. I'm collecting travel diary over a week, and suppose that I'm interviewing myself this week, right? So this is me, Cinzia Cirillo, and suppose that I was given a travel diary to describe my week here in Taiwan. So what happens is that on Monday, what I'm doing is hotel, school, and I'm walking, right? On Tuesday, I'm doing hotel, school, and I'm walking. On Wednesday, hotel, school, I'm walking, and on Thursday and Friday, I'm doing exactly the same. Right? Now, logit does not recognize. Logit says, well, Cinzia Cirillo gave 5 observations, and it does not recognize that it's always me. So it assumes that these observations are independent. However, this is always me, always in Taiwan, always giving lecture in the morning from 10 to 1, and always walking to this place, right? So there is correlation across my observation. And so forget to do this, to account for this correlation effect in logit. You cannot do this with logit or nested logit. You need to use probit or mixed logit. Now, this is kind of exaggerating in the sense that this week I'm doing the same every day. But in normal life, you don't have the same schedule every day, right? One day you are coming to school, another day you are going to shop, another day you eat out with friends, another day, so there is variability in travel behavior. That's why we collect weekly travel diary. right? Because we want to know how your week is organized, how your Monday is different from your Friday, how your Wednesday is different from your Thursday. And this is especially true in modern society. For example, I'm always mentioning my work in Europe. When I was in Belgium, we collected the National Household Travel Survey, and we realized that travel pattern were kind of different from, and this is because in Europe now it's kind of part-time jobs. Many people are working part-time. For example, in the Netherlands, half of the population are working part-time. It means, for example, that these people have either the Friday off, or on Wednesday they work just half day, just 4 hours. So it means that because these people are working less on some days, they are not traveling on that day, or they are doing other activities. So, and you can understand this if you have panel data, weekly panel data, and if you realize that travel patterns are different from day to day. So that's why this dynamics is very important, and that's why sometimes we need advanced discrete choice models, right? So is this clear? Because although it's very descriptive, it helps you to understand why we need these advanced discrete choice models and what we can do that is more than what we used to do before. Let's see now with a more structured example what I was saying. So this is taste variation. So Logit can capture taste variation with respect to observed variables, while random taste variation cannot be handled. That I already said that. For example, this is another example. Consider household choice amongst makes and models of cars. So this is a case in which you want to buy a new car, right? And you have plenty of choices. You have plenty of makes and plenty of models, right? So the utility is function of shoulder room. So if you are a big guy, you need a big car, and of purchasing price, right? So suppose that this alpha varies with the number of members in the household. So this coefficient alpha is kind of function of the members in the household. So I can say that and beta is inversely related to income. Because the more income you have, the less you are sensible to price, right? If you have a lot of money, well, you are not very sensible to price. You are willing to spend a lot on your car. That's why it's inversely proportional, right? So it means that this changes into shoulder room interacted with the members of the household, and purchasing price interacted with income. So this is the way we can handle deterministic taste variation for that case. But now suppose that the value of shoulder room and purchasing price varied with observed components plus some factors that are unobserved. So the example before, it's like, you see that here there is no unobserved term. So we suppose that alpha varies deterministically with m, right? So we say alpha is a function of the number of people in the household, and that's it. There are no unobserved terms there that we cannot observe. Which is the difference here, right? Because alpha now varies with the number of members in the household plus kind of something that we cannot observe. And the same with beta, which varies with income plus some unobserved terms, right? So by substituting everything into the utility, what happens is that we have this term like before, we have this term like before, but we have some additional terms here. And these additional terms, they all go into the error term, right? So we have the error. We have a new error term, which is much more complicated than the error terms before, which was just this. And so we have two additional error terms. The problem is that these error terms, they depend on shoulder room and purchasing price. So this new error term is not independently and identically distributed as in the Logit formula. So in that case, we cannot use Logit anymore because the IID properties is not there anymore, right? That's why you need for this random taste variation. So this is the difference between the deterministic taste variation, which is this, right, as a function of something that you know, and this, which is function of something that you don't know. There are additional error terms there. And these error terms are correlated with existing variables. So the IID hypothesis is not something that we can assume. And so Logit is not a good formulation for this kind of problem. Right? All right. Okay, so this is the problem number one, taste variation. So the difference, yes?
Yeah, can you go back to the previous slide?
Yes.
So what if we estimate, for example, the income and purchase price separately instead of jointly? So how? Yeah,
this is a difference in the way you are estimating the model. So when you estimate, so it's like U gas and U electric, right? So it's like beta purchasing price multiplied purchasing price plus beta income multiplied by income, right? That's what you want to do. Instead of interacting I with purchasing price, you have this as another factor. Well, these are two different specifications because this is affecting the marginal utilities of having a gas heating system, but it's not telling you that there is a taste variation with purchasing prices depending on income. So it's just affecting the marginal utilities of buying a gas heating system, but it's not telling you anything about taste variation. So it's true that you can do both, but we prefer always to have this interacted with price or income interacted with travel time, because this will give you indication of taste variation. So you can do this, but this is going to tell you just about the influence of income on the utility of purchasing a gas heating system, instead of telling you something about the taste variation. And the interaction is much more useful in policy application because it tells you how the willingness to pay varies with income instead of how income affects the utility of buying a gas system.
Okay. I'm just curious about, you make an assumption about the relationship between income and the purchase price.
Mm.
So you state a function layer beta n, right?
Yeah.
So what if we do the separate estimation first, then we compare their coefficients?
Well, but this coefficient will be very different from a coefficient in which you interact the two. Yeah, you can do this, but the objective is different. So it's what you want to do here, you can do it, but the objective is different. So my objective is to estimate taste variation. And if you have this formulation, this doesn't tell you anything about taste variation. It's just another coefficient estimated, which is a good coefficient. It's going to very likely to improve your livelihood, but it's not telling you anything about taste variation. So given that one of the properties that we have seen of this kind of random utility models is that the probability of choosing all the alternatives sums to 1. This is the definition of probability, right? It means that if you increase the probability of one alternative, necessarily there is another alternative who will see a decrease in the probability of being chosen, right? So if you increase the probability of choosing public transportation, probably it's because the probability of choosing car is decreasing, right? However, when you estimate a Logit models, this ratio, right, the probability of choosing I divided the probability of choosing K, just depends on the difference between the systematic utility of I and K. So if there is a third alternative, for example, J, this alternative does not appear here, right? And this causes a number of problems like the red and blue bus problem. And this is exactly the independence from irrelevant alternatives, or IIA. Now, this is something that we know that when correlation exists among alternatives, this is something that we don't want. And so that's why we go to nested logit, we go to probit, and we go to mixed logit, right? However, this is a very good property when we are in some specific situation. And in particular, Logit model is very good when you need to estimate models on a very large set of alternatives. So let's try to understand when this property is a good property. So I have at least 2 examples. Maybe you have more. But this is a very desirable property when you work with destination choice model. What is destination choice model? Destination choice model is, for example, when you need to estimate, starting from a given origin, where I'm going to be, where I'm going. Suppose that this is type A, and type A is divided in my, type A is my study area, and suppose that in type A I have 1,000 zone, right? Suppose that this is my origin. So the second step of my 4-step model is destination choice model, and we calibrate this with discrete choice models in the good models. I always tell this to my students. For example, the Maryland statewide model is just a gravity model, not good. So they should redo it and with discrete choice models. And so my model will say, well, I need to specify an utility for myself, from my origin, to each destination. But I have, given that I have 1,000 possible zones in Taiwan, and given that sitting on my desk I have no idea where you are going, all these 1,000 destinations are possible. So I need to specify an utility for these 1,000 OD pairs. And this is, believe me, a nightmare. So instead of doing this, what we do is, instead of working with 1,000 destination zone, is we select the chosen zone, because remember that I asked you in the National Household Travel Survey, where did you go yesterday? And I told you, I'm going to school to teach, right? So I select the chosen alternative, plus I randomly select a subset of the alternatives. So instead of working with 1,000 alternatives, I can select, for example, 20 alternatives plus the chosen alternative, and instead of specifying 1,000 utility, I will specify just 21 alternatives. And given that there is this IIA hypothesis, I know that my coefficient will not be biased. So this is a very nice property of Logit. So this is the same, I believe. So you see that probabilities within a subset of alternatives are unaffected by the attributes or existence of alternative in the subset. So exclusion of alternative in estimation does not affect the consistency of the estimator. So I will have unbiased coefficient. Another example that you will see the results of this student of mine has just done is the problem of make, models, and vintage of cars, right? When you want to buy a car, or you have a choice amongst a very high number of alternatives, because you can buy a Japanese car, you can buy a Korean car, you can buy an European car, you can buy an American car, and you can buy a small car, a large car, an SUV, a truck, and you can buy a new car, or you can buy a 1-year-old car, and 2-year-old car, and 5-year-old car. So the combination of this will give you a very large number of alternatives. So instead of, and you need to specify the utility of all these alternatives. So you need to know the characteristic of all these cars, right? Because a small car will be different from a large car. The MPG of a new car will be very different from the MPG of an old car, and so on. So instead of working with, I don't know, 200 combination of this car, you work with the chosen alternative, because you know which kind of car you have, always from the NHTS, because there is a section on cars. And then you select randomly, for example, 10 alternatives, 20 alternatives, and this will be enough to have your coefficient estimated. And we do this many times and with very good results. So this to tell you that this IIA property sometimes is something that we don't want when we have correlated alternatives, but sometimes it's good. And there are studies that say that, actually there is a paper from Professor Chandra Bhatt saying that you cannot do the same with mixed logit. So mixed logit is nice, but it's something that you don't want to use when you have a very large number of alternatives. It's better to stay with logit because of this property. So this is one case in which using advanced discrete choice models is going to produce worse results than classical and old-fashioned logit model.
Previous slide, you mentioned about the consistency of the estimate. How about the efficiency? Because you only use a subset of your alternative. Will it be effective?
So the efficiency will be the variance. I don't know. I know that the coefficient will not be biased, so I needed to go back to this. I don't know. So remember that usually discrete choice models, so this is kind of different concept, but okay, remember that discrete choice models, usually the utility in discrete choice models is linear. So usually the specification is always a linear function of the attributes, right? So we are working with beta multiplied travel times plus beta cost multiplied travel cost plus, right? So this is V. So this is a linear combination of the attributes, right? Then you estimate the same model on a subset of the alternatives, and you have another set of coefficients. You compare the two sets of coefficients. If they are similar, it means that IIA holds, and then you can work with logit. If they are very different, then it means that IIA does not hold, and you need to go for a more advanced specification. I will save this for later because I needed to say what is mixed logit with correlation. The problem with this, so suppose that this test failed, right? So suppose that you get a different set of coefficients estimated in the two trials, right? The full model and the model estimated on a subset. So the problem of this is that there is, you know that IIA does not hold, but nobody's telling you which is the good structure, right? So for example, if you have a large number of alternatives, suppose that you have bus, train, you have high-speed train, you have tram, you have metro, and you have car as a driver, and car as a passenger, right? So these alternatives are very likely to be correlated. So if you test this IIA here, it's very likely that IIA does not hold. The problem is that what you know is that this does not hold, but nobody's telling you which is the good correlation structure. So nobody's telling you if bus is correlated with metro and tram, if these two are correlated, so you need to try. And this is one of the problems of nested logit or mixed logit with error component. You need to test a number of structures. That's also the problem with this advanced form of discrete choice models. So nobody is telling you exactly which one is the good one. You need to test. And especially if you are waiting for results from mixed logit, they take hours. And so it's a very time-consuming task. So that's why they are nice, but sometimes they are difficult. OK, so this is panel data. And as I was saying, the problem is that independence over repeated choices that cannot be handled with logit. And so any dynamics related to, what I want to say, again here, logit cannot handle correlation effect related to unobserved factor. It means that you cannot account for correlation. So logit cannot handle for correlation across unobserved factor. So cannot handle the correlation that exists. For example, in my, so on the epsilon of myself, Cinzia Cirillo choosing to walk on Monday, and the epsilon of Cinzia Cirillo walking on Tuesday, right? So this is what logit cannot see, the correlation amongst unobserved factor, right? But what you can do is you can specify dynamics in the observed factor. For example, you can say on the utility of Tuesday that the mode chosen was walk, right? So you can specify kind of inertia variable. You can account for the choices of previous periods in the choice of the current period. That you can do this. So you can actually use dynamics of observed factor can be accommodated, right? You can use the fact that I'm always walking to come to school in the morning. But what you cannot do is dynamics associated with unobserved factor. So everything is correlation on epsilon. You cannot do with logit, but you can account for correlation amongst factors in B. Can you see the difference? So for example, you can use these inertia variables or lagged variables. For example, lagged price responses can be the price in period times -1. So suppose that you are specifying the systematic utility of individual n for alternative j's and time t, right? So this can be function of the choice in previous period, right? This is y n j t -1. So for example, my choice of walking today is a function of my choices of walking yesterday or the day before yesterday and so on. Or for example, I'm buying a product today and the price that I'm paying is a function of the price of that product yesterday. For example, in the auction market. However, lagged dependent variables can be added without inducing bias if they are not correlated with epsilon and jt. So be careful with that, because these lagged variables, because if these lagged variables are correlated with epsilon, then you introduce bias in our coefficient. And so you are messing your model. So you can do this as long as there is no correlation between the errors and the slugged variables. So remember that usually discrete choice models, so this is kind of different concept, but okay, remember that discrete choice models, usually the utility in discrete choice models is linear. So usually the specification is always a linear function of the attributes, right? So we are working with beta multiplied travel times plus beta cost multiplied travel cost plus, right? So this is V. So this is a linear combination of the attributes. And usually that's what we do. In the past, we have tried quadratic, for example, travel time squared, or Box-Cox transformation that are nonlinear transformation. However, we always go back to this linear specification of the utility. And this is because estimation is much easier, and also because we see that by having a more complicated utility function doesn't make much difference. So in transportation, usually we have a linear combination of the attributes. There are exceptions, and one of these exceptions is related to destination choice model. So destination choice model is the model that I was describing before, is when I need to calibrate a model that is telling me, given an origin where I'm going, it's going to predict the destination of my trip. Now, this, when you specify the utility of destination choice model, what happens is that you have, of course, time and cost in the utility, right? You will specify travel time to that destination plus travel costs of that destination. But what you have is also some attraction variables. It means that I'm coming here because there is a university and there are many people here, and so this place for me is kind of an attraction. So how am I modeling the fact that this place is attractive to me? For example, from the number of students who are here or the number of workers in this building, right? For commuters, for example, many people are going downtown to work because there are many jobs there. Or for shoppings, a place is attractive because there are many shopping malls or there are many shops around, so these places are attractive. So these variables, number of jobs in education, number of jobs in banks, number of jobs in the retail system, etc., are called attraction variables. So these attraction variables are used both for destination choice model and for residential location. Residential location is also another very popular models nowadays. You see many papers published. So it's how I'm choosing to locate myself, where I'm going to buy a house, for example. And these attraction variables for residential location help me. Give me an attraction variable for residential location. What can that be? For example, number of good schools, right? If there are good schools, I want to be there, especially in the US, because I want my kids to attend a good school. Or for example, shops. If there are shops that are very attractive, I want to live there. If there are many green, if there are green parks, I like there, I want to be there. So these are attraction variables. However, these attraction variables, you realize that these attraction variables depends on how large is a zone that I'm considering, right? So suppose that this is type A. So I can divide type A in 12 zones, or I can divide type A in smaller zone, right? So the attraction variable will be different depending on how large or how small are these zones. However, I want my model to be independent from the way I've divided my zones, right? So I want the model that is not sensitive to the level of aggregation in the zonal definition, right? So I want a model to be able to predict the destination if I'm dealing with a small zone or large zone. So it means that if I have a large zone that is the sum of two small zones, right? So if C is this is C, and this is I and J, I want the model to be able to predict C or I and J independently of the size of these zones. So in reality, I want that if C is composed of zone J and K, I want that the probability of choosing J plus the probability of choosing K is exactly the probability of choosing C. That's what happens, right? When you choose a destination choice model. So this is the way I'm constructing my logit model, right? And this holds only if this holds. So it means that in order to specify a destination choice model that is not sensitive to the level of zonal aggregation, the utility needs to be specified with a parameter inside the log operation. So this is a famous paper from Andrew Daly in which he defines these attraction variables, and this shows exactly this. So it means that all these attraction variables needs to be in a log operator. For example, number of jobs cannot be, so it means that, suppose that this is a destination choice model. So usually you will say number of jobs in D, right? This is wrong. What you need to do is you need to say plus log of number of jobs in D. This is the right one. This is wrong. So this is a case in which the linear specification is not a good specification. You need to go for a different specification which is nonlinear and which has a log here. If you have a log for the attraction variable, then everything holds, and the probability of choosing a destination doesn't depend on the size of that zone or on the level of aggregation of your study area. Right? So this is a paper from Daly in the 80s. But it's very important because I've seen many papers from PhD students that actually have this problem, even PhD students from the US. So, so it happens. So you need to know, and these residential choice location model are very popular nowadays. You know, Urban Sim, for example. Do you know Urban Sim? Urban Sim is a very popular model system for land use and transportation planning together. And this base, many of these models in Urban Sim are residential choice location, destination choice models. And so there is a lot of research going on in residential choice location or destination choice and so on. And remember that this is the good way to estimate them. Okay, so so at the end, to summarize, linear utilities are always good. Don't bother about quadratic, another form, except in this case, in which you need to have a log operator for this variable. Now, so far we have seen how to estimate these models, right? How we calculate the probability, how we read the betas, and so on. But there are actually, the beauty of these discrete choice models is that you can actually use them in order to evaluate policy, and you use them in four-step transportation model and so on. And also for the nice interpretation of this utility, and in particular in terms of consumer surplus. So when, so kind of the calculation of consumer surplus kind of translate the utility in dollars terms, for example. So utility has no, utility is utility. It's not in dollars, it's nothing. It's just utility, right? However, if you calculate the consumer surplus, you can kind of get an idea of in dollars or in money terms of the utility. So for example, by choosing the car, I'm getting an utility, but this utility can be transformed in consumer surplus. So in dollar terms, can be translated. At the end, everything is about money, right? Especially in the US. And also, the nice things about these discrete choice models is that when we use for policy analysis, we have a before policy situation and after policy situation, right? So we want to be able to say, well, what changes for me if I'm changing these attributes in the transportation system? For example, before building the high-speed train, I had a consumer surplus by choosing train. Now I'm switching to high speed, I'm paying more, but I'm also deriving something. So I want to compare the consumer surplus before the high-speed train and after the high-speed train, right? For example, if a new alternative is included in my transportation system, for example, I'm building a light rail system in a city, then it's important to measure the benefit of the project to see if it's worth to spend that money on that project, right? So if that's the problem, for example, now in the United States. They say, well, we don't need the high speed because, well, it costs a lot of money, and there will be not many people who are going to use this. So this is the kind of application. You need to measure the consumer surplus before and after and see if it is worth to build that infrastructure. Or, for example, for something that already exists, for example, you are improving travel time on the bus. So you will measure consumer surplus before and after, and you'll see how much is the gain for all the people who are taking the bus. So you see that the consumer surplus is 1 divided alpha n. Alpha is the coefficient multiplying the cost, because you see that because 1 over alpha n is transforming everything in money, in dollar unit. And this is the max of the utility of choosing J. And alpha n is the marginal utility of income with y and the income of person n. So as I said, the division by alpha n translates utility into dollars. And the problem is that this is the definition of the consumer surplus, which is function of U. However, in transportation, what we estimate, what we observe is V, is not U, right? So what we kind of calculate is the expectation of this consumer surplus, because it's the max between the sum of V and epsilon. So if you use a logit model for your discrete choice model, you see that the expectation of this consumer surplus has a very nice closed form, which is function of alpha and of the ln of the sum of the utility. So, well, this is C. Is just the scale of the utility. Remember that we do not observe the absolute scale of the utility. So everything is on differences. That's why we measure the consumer surplus before and after, because there is an absolute scale of the utility that we not observe and that is included in this C. So what is nice is that this, remember this is exactly the denominator in the choice probability of logit. So this is very nice. And so the consumer surplus is simply the log of the denominator of the choice probability. and it's called the log sum, right? It's the log of the denominator of the choice in logit models, so it's called the log sum. So the consumer surplus depends also on the segmentation on which you have divided the population. So, and this is very nice because if different segments are present, you can calculate the weighted average over the segments, or you can calculate the changes in consumer surplus for different segments of the population. For example, a nice application that we have done of this is that we were analyzing accessibility to the transportation system of low-income population, right? So we have divided the population into high-income, medium-income, and low-income population, and we have calculated the consumer surplus for each of these three segments. And what you can see is you can see the consumer surplus of these three segments of the population to the transportation system. So you can clearly see that by, well, if you apply a policy, these three segments will have different changes in consumer surplus. So this is what is very nice about this consumer surplus. So another thing that it's possible when you work with discrete choice models is calculating elasticity. So what is elasticity? Elasticity is the change in probabilities due to a change in some observed factors. And in particular, you have direct elasticity and indirect elasticity. So what is direct elasticity? So direct elasticity is change in the probability that decision maker N chooses I given a change in an observed factor of this alternative, right? So the change in probability due to a change in the observed factor of this alternative. And this is the direct elasticity. Well, if you do some algebra, usually I do that in Maryland, but here I don't have the time. This is what you get, right? While if you want to calculate the change in the probability of choosing an alternative due to a change in the attributes of another alternative, that's why indirect probability, indirect elasticity, that's what you get. You see that here you have the operator, you have the index I, and here you have the index J. So change in probability of alternative I due to a change in the attributes of alternative J, and this is what you get, right? So this is a function not just of probability of choosing I, but also of the probability of choosing J. So this is direct and indirect elasticity. For example, if you have a model in which you are comparing car against public transportation, an example of elasticity of choosing car with respect to fuel price is that you calculate the change in probability of choosing car with respect to the changes in fuel price, right? So this is direct elasticity. Another indirect elasticity is when, for example, you want to calculate the changes in the probability of choosing public transportation given that the fuel price is changing, right? So this is also an a way that you apply discrete choice models to calculate elasticity. Now, this is something that you won't see when you use discrete choice models, but it's something that the software is doing for you, right? It's the estimation. So usually if you are a user of discrete choice models, what you do is specifying this V. So you specify this V, you give to the software, and the software is giving you back this beta. But what's going on there, it's an estimation. And so the hypothesis under which we estimate the discrete choice models is that usually we say that the data is random, and that's what makes everything simpler, and that's what makes you the possibility, gives you the possibility to estimate maximum likelihood procedure. So either it's random and everything is fine. So random means that you have randomly drawn your sample from the population, and that's what happens with NHTS. Or it's sometimes stratified, and for this you need to apply more complex discrete choice models. But usually it's random. So we can assume that our sample is randomly drawn from the population. And actually we assume that the population is a very large population, is infinite population. We also assume that the explanatory variables are exogenous to the choice situation. And so we can apply maximum likelihood procedure to estimate the model. And actually, this is the likelihood. And actually, this is the choice operator. It's 1 if the person N chooses psi and 0 otherwise. So this is the choice. This is the likelihood. Actually, this is the probability. So you write down the likelihood. So this is the product over all the observation, right? N's are the observation in your sample. This is the product over all the alternatives. And this is the probability of choosing the alternative, and this is the choice operator. So this is the likelihood. You write down the likelihood. Then you transform this into log likelihood because it's much easier to work with sum instead of working with product. And then you maximize this log likelihood, and that's how you can get the beta, because this probability is function of the beta. So by maximizing this, you get the beta at the optimal. And you can see that in Logit, you can demonstrate that this is globally concave for linear in parameters utilities. And it means that you have just one optimal solution, and you are sure that the betas are unique. Now, why I'm saying this? For a number of reasons. Now, if you just use Logit, nested Logit, you don't bother to know which is the likelihood or the log likelihood. But when you work with more advanced models, in many cases, you need to write down the log likelihood, and you need to maximize that log likelihood, which is not an easy task. So if you want to work with advanced models, be prepared that you need to deal with this kind of stuff. So you need to write down the log likelihood, and you need to maximize very complex log likelihood. Now, Logit is the only case in which you can demonstrate that this is globally concave, and there is one maximum. But already, if you work with nested Logit, this is not true anymore. So you have possibility of local optima and so on. All kinds of strange things can happen. Estimating a probability is extremely difficult. Estimating a mixed Logit is also very difficult because at the maximum, the function is very flat. And so you lose a lot of time maximizing that log likelihood. And the other thing is that before, given that we were working with this function, which were relatively easy to estimate, linear search was, Newton-Raphton was good enough. Now, I will say that you need a better optimization method in order to estimate this. And actually, I think one of the reasons why I'm in the US is because we have implemented trust region method instead of linear search in order to estimate this log likelihood in mixed Logit. So what I want you to know is that that's why Logit is still used, and it was so popular. It was because also the optimization was kind of easy. And the fact that there is globally concave and there is one optimal, it made everything easy. Now, if you want to estimate a probit or a mixed Logit, you need to write down this log likelihood. It's different for each problem, and the estimation, the optimization is very complex. And the same properties that hold for Logit, they do not hold, for example, for mixed Logit or for probit. So this is making our life much more complex. I also want to give you some indication about how we assess that a model is good or not. Actually, I was just reviewing a paper yesterday, and it was for a very good group of research, and however, they were making some mistakes in the way they were reading the statistics of the models. So if you send a paper for review, you want to be sure that the interpretation of the statistics is done the way it should be. I will show you some models estimated, so we will learn how to read the statistics that the software delivers. So we use the likelihood ratio index to measure how well the model fits the data. And in particular, the likelihood ratio index is used to compare models, right? Usually we compare, for example, the model estimated with some coefficient with a model that has, in which all the coefficients are 0, right? So a model in which you explain something with respect to a model in which you don't explain anything. And so this is what we do, for example. This is the log likelihood, the final log likelihood at the estimates. You see, this is the vector of estimates, and this is the log likelihood at 0, right? And in particular, we use the rho squared, which is 1 minus the log likelihood at the coefficient minus the log likelihood at 0. So you get something that is between 0 and 1. 0 is when you don't explain anything. So having the beta or not having the beta is exactly the same. And 1 when you have a perfect model in which you explain everything. In reality, you never have 0 and you never have 1, but you have something in between. Okay, now, don't make that mistake. That was the mistake of the paper I was reviewing yesterday. They said, well, we have a 0.4. This is a good model. No, having 0.4 doesn't mean that it's a good model or it's a bad model. You can just compare the 0.4 with another model that has a different rho squared. So you can say, well, this model has a rho squared of 0.4. The same model, the model estimated on the same data, but at 0.3, so it's better than the previous one. So you can just compare different rho square. Another thing in my profession, for example, I was working for a company, and when they saw the results of my models, they said, oh, your models are not good. You have rho squared of 0.1, 0.2. They said, this is really not good. We should get 0.7, 0.8. And I said, remember, this is not regression. This is discrete choice modeling. So you will never see 0.7 or 0.8 out of this model. You will see very often 0.1, 0.2, but this doesn't mean that your model is bad. Actually, a low value of this rho means that you have a very complicated model. And by estimating more of this model, you will see that the more alternatives you have, the lower your rho squared. It's because it's very difficult to recover the choices. Because if you have many alternatives, it's very difficult to recover the choices, and it's very difficult to recover the choices that have low probability of being chosen, right? You make big mistakes on the small probabilities. That's why your rho is low. And actually, from the paper yesterday, it was 0.4. I said, well, this is a binomial logit, just 2 choices. That's why you get 0.4, right? Okay, so, but I spent a couple of days explaining to this company that they should not expect 0.7, 0.8 from my models. Actually, this is the paper, this is the slides that these people from the paper should have seen. Sometimes people, and this is also a statistic that is delivered by Biogym in the earlier version. I don't know if he's still using that. So they use this percent correctly predicted. But this is something that you should avoid. I never use this. And this is clearly explained in both Ben Akiva Lerman and Train, that you should avoid this measure. This is not telling you much. Use the log likelihood ratio test, use the rho squared to compare models, but don't use this. This is something that is misleading. So this is percent correctly predicted how it works, these statistics that I don't want you to use. I'm just telling you this to say don't use this. It works that you calculate for each sample, for each decision maker in your sample, you calculate the alternatives with the highest probability, right? So you apply the model, and for each individual, you calculate the alternative with the highest probability. And you see if this was the chosen alternative, right? So it's assuming that the choice with highest probability, you compare the choice with the highest probability to the chosen alternative. And that's what makes, and then you calculated the percent correctly predicted, right? So you are able to calculate these statistics. So these statistics will tell you if the alternative with the highest probability will be chosen each time. But this way to calculate these statistics is misleading because remember that the model is not predicting the chosen alternative. It's not telling you which is the chosen alternative. It's giving you the probability of choosing an alternative. So that's why this statistics is not good, because it forgets kind of the probabilistic characteristic of these models. So this is not a good way to test the goodness of fit statistics. So forget about this. Use the previous one, this. What you want also to test here, sometimes what you want to test if two coefficients are equal or not, right? For example, what does it mean? It means that, for example, say that I have one model in which I say this is beta 1 multiplied travel time. Say this is car, and this is travel time by car. And then I have public transportation that has beta 2 multiplied travel time by public transportation, right? So it means that I'm estimating the model with beta specific to the alternatives, right? I'm saying that travel time by car is different by travel time on public transportation. Now, I want to test if beta 1 is equal to beta 2, right? So if this is true, I can go back to a model that says that V car is beta travel time and VPT is beta travel time by car and by PT, right? I can have one beta. So this is what I want to test, right? And so I will compare the log likelihood, the final log likelihood with this model and this model. And so I will calculate this minus 2 times the log likelihood of the complex model minus the log likelihood of the simple model that contains one beta. And I know that this is a chi-square distributed with degree of freedom equal to the number of restriction. Here I have one restriction, right? I'm restricting the 2 coefficients to be equal. I have one restriction. And so if this value exceeds the critical value of the chi-square distribution with the appropriate degree of freedom, then the null hypothesis is rejected, right? So I can say if this difference is greater than the chi-square distribution with degree of freedom equal to the number of restrictions, then I can say that it's worth to have beta 1 and beta 2. If it is less, then I will go for one coefficient, right? All right. So this ends my slides, and I wanted to show you some practical models estimated to give you an idea of what we get. So this is nice, but we want to see some application, right? To see how to read this result. All right, so these are just examples taken from Ben Akiva Lerman. This is what I show to my students because I think they are very instructive. It shows you how to build a model, how to read the results of the model. So this is just binomial logit. You see you have two alternatives, auto utility and transit utility, and you have just two coefficients, alternative specific constant. So you just have one alternative specific constant for the car, and you have travel time. So you expect two coefficients to be estimated, right? Alternative specific constant of the car and the travel time as a generic variable for both car and transit. So this is an example of your database, right? So you have the observation. In this database, you have very few observations. You have 21 observations, right? Usually, I don't know, usually we have from stated preference, say, 200 individuals. Each of them gives 10 choices, so 2,000 observations. From RP, we have usually 1,000, 1,500, depends on your problem. So you see that you need to construct the travel time for the car and for the transit independently of the choice, right? So usually this comes from, these numbers, they come from a traffic model, from kind of a simulation model in which you have all the car network and the public transportation networks, and you are able to see which is the travel time from the origin of this guy, number one, to the destination of this guy. So you will see that here, this is a very bad example. I don't know why Ben Akiva has this in his book, but you see that by car it takes 53 minutes, and by transit it takes 4 minutes. So I don't know where this problem is, but this is what he has. And you have the choice, right? The choice is transit, of course, because it takes 4 minutes compared to the 43 minutes. And so this is the data set. This is kind of to give you an idea of the estimation of the likelihood, right? So you start from, this is the log likelihood with the number of iterations. So finding the optimal of the log likelihood is an iterative process. So you start from this, right? The log likelihood at 0. What does it mean? It means that both coefficients, they are 0. So the alternative specific constant and the travel time are 0, and this is the value of the log likelihood at 0. That's what you will see on the output of the software. At the first iteration, the value of the betas are minus 0.061 and minus 0.28, and this is the value of the log likelihood at the first iteration, right? The second iteration, you have a new value of the betas, third iteration, fourth iteration, and fifth iteration, and these are the final values of the betas, and this is the final value of the log likelihood, right? So that's what BioGym is doing when it's estimating your betas. All right, these are the values. You have a value for the alternative specific constant and a value for the travel time. You have the standard error and you have the t-statistics. So the check when you estimate a model is, am I getting the right sign? Are the coefficient significant or not? And the log likelihood ratio test. So let's see this. So travel time, what we expect about travel time? A negative or a positive beta? Negative, why? Because it's a disutility, right? So the more travel time, the less I like this option. So this is good. Actually, we like coefficients that are significant at 95% level of significance. So it means that this should be greater than 1.96. So this is significant, this other one is not significant, right? We keep it because it's the alternative specific constant. So that's why we keep it into the model. But this is significant, this is not significant. This is the summary of the statistics. That is what you get when you estimate a model with BioGym. So you have the log likelihood at 0 when both coefficients are 0. This is the value. This is the log likelihood at constant. It means that just constant are included into the model. Here, just one constant is included. So you see that you are improving, but not much, right? And not much because this is not significant, right? And this is the log likelihood when all the vector of the coefficient is estimated. And you see that you are improving a lot. From 14, you are down to 6. And actually, you can do the log likelihood test, and you can compare the estimated model with a model with 0 coefficient, or the estimated model with a model with just constant, right? These are the values that needs to be compared with the chi-squared at 95% level of significance, and with degree of freedom 2 in this case and 1 in this case. And for sure, these are, you can reject the hypothesis that the betas are equal to 0. And so you are making significant improvements when you have the travel time estimated. And these are the rho squared. You see, magically, the binomial logit, what I was saying, it gives quite high rho squared because it's relatively easy to estimate. You just have 2 alternatives, and so it's easy to estimate, and that's what you have. You have about 0.4. All right, now this was the, so I always suggest that you start with the logit with alternative specific constant and travel time, right? So this is alternative specific constant plus level of service variable. Now, but of course, this is not the specification, the final specification. We want a better specification, right? So what we can do is, for example, divide the travel time into a different component. So here what we are doing is that we have both in-vehicle travel time and out-of-vehicle travel time. So we don't have the total travel time, but we separate the travel time into 2 components, and we have different betas. You see that this is greater than this, and we always say in transportation that out-of-vehicle travel time is more negative than in-vehicle travel time. We hate to wait, we hate to walk, and so on. So that's why this is much greater than this. This is cost. Remember that cost is out-of-pocket cost. So it's exactly what you pay for fuel and what you pay for fare of the transit. It's not considering insurance or the price of the car and so on. It's just out-of-pocket cost. Actually, Ben Akiva estimates 2 costs, one for car and one for transit. I don't like this. So I suggest to have 1 cost, because the cost is the scale at the end of the model. So if you scale with just 1 cost, you will have different travel times and 1 cost. Otherwise, this will make everything complicated for the calculation of the value of time. So he was doing this, but I suggest to have different travel time component and 1 cost. Then you have some social demographic, right? This is actually the number of cars in the household specific to the auto mode. And you have the downtown workplace, so if you work downtown. And these are specific to the car mode. Remember that you cannot estimate alternative specific constant in all the alternatives because they will not change the utility. Can you see that? Because it's always the same variables. It does not change across the alternatives. So you cannot estimate. So you need to have them specific of 1 alternative. Right? You see the log likelihood at 0. It's when all these coefficients are 0. The log likelihood at the vector of beta parameters, you see how much this is improving. So this is explaining a lot of behavior. This is the log likelihood ratio test. You see that this is a very high number. It's for sure greater than the chi-squared critical value for degree of freedom 2, 4, 6, 7. And this is the rho squared. Again, a very high you see that you improve. So now you can compare this rho squared, and in particular the adjusted rho squared that take into account the degree of freedom with the previous one. But you cannot say by just looking at this, oh, 0.6 is good. Doesn't mean anything. So you can compare the 0.6 with the 0.4 that we obtained before and say, this is a better model than the one before, right? So all these are comparative measures. Remember that in discrete choice models, only the difference in utility matters. So it's always a game of comparing things. So the absolute value, they have no value, right? All right, so this is the first set. Okay, so this is another example in which you have 3 alternatives. So it's always good before you start to estimate a model to understand a little bit what is behind this data. So for example, here you have a number of descriptive statistics. So I always tell my students, when you start with a new database, try to understand what's going on in your database. So you want to know the market share. You want, for example, here you have that drive alone is chosen by about the 27%. Shared ride is used by 37%, and the transit by 56% of the population. So try to learn about the data. Try to understand what's going on. So you have some statistics about average travel time, out of vehicle time for drive alone, shared ride, and transit. Average travel cost. See, this is average travel cost in cents, I think. The distance, average household income, number of cars in the household, number of workers in the household, and number of persons in the household. Try to have descriptive statistics. Try to learn from your data, because this will give you a better model. Okay, the specification, what do we have here? So this is a logit with 3 alternatives, right? So we expect 2 alternative specific constant. So we have drive alone constant and shared ride constant. It means that transit is the base, right? So the alternative specific constant of transit is 0, and the other 2 are estimated. So given that transit was the alternative most chosen, right? It was 56%. We expect negative signs for the alternative specific constant of drive alone and shared ride. Okay, so that's what we expect. We have travel time, and we have, okay, this is also a bit strange here, but you know, we take this for granted. So we have total travel time, and we have out of vehicle travel time. So it's kind of double counting, right? Because out-of-vehicle travel time is also included in in-vehicle travel time, which gives us a little bit of trouble when calculating value of time. And this is divided by distance, actually in 0.01 per mile. That's why you have this big number here, because it's divided by distance. They are both negative, which is what we expected, right? They are both travel time component. Let's see, they are kind of, this is kind of not significant at 95% level of significance, but it's more than, well, it's okay. It's close to 1.9. And then we have a number of social demographics, which is cars, number of cars per workers. It means this gives you an idea if a car is available to all the workers in the household, right? Now, in the United States, this is a very old model, but now in the United States, we have 1 car for each worker. So we can just say number of cars in the household. And this is specific to the drive alone and shared ride. This is downtown workers place dummy specific to the drive alone and shared ride. This is income. And this is income the way you wanted to specify it, right? It's not interacted with travel time, but it's just including in the utility alone. And this is also specific to the drive alone and shared ride. And this is if you work for the government, and this is specific to the shared ride, because at that time, in 69, I think this model is from 69, many people were sharing the ride because they were working together, and so they were likely to share the ride to go to the same workplace, right? And in fact, this is positive and significant. Again, log likelihood at 0, log likelihood at constant, and log likelihood at the coefficient estimated. And you see that this is a very high number, so for sure these betas are not equal to 0. And you start to see that this is 0.3. This, again, doesn't mean that it's a bad model, but it just means that it's a model that is more difficult than the previous one because we have 3 choices here instead of just 2, right? Okay. This is the variance-covariance matrix. This is also very important because it's going to tell you if there is correlation across coefficient. And I think here there is nothing problematic, but if you start to see values that are 0.7, 0.8, it means that there is high correlation across coefficients. So you might want to see why this is happening, and you might want to get rid of some of this coefficient if there is high correlation. For example, what happens in very often in model estimated from revealed preference data is that there is high correlation between travel time and travel cost, right? It's why this. This is one of the problems with revealed preference data, and that's why we want stated preference sometimes. So what happens is that when you estimate, when you calculate the attributes, right, from NHTS, so you ask people, what did you do yesterday? They say, well, from home I went to school and it took me 30 minutes, right? But they are not going to tell you how much it cost. So what you do is, well, it took 30 minutes, she was traveling by car, so you calculate travel costs based on distance. But travel time is also based on distance, so it means that both travel time and travel cost depends on distance, and so it is very likely that travel time and travel costs will be correlated. So check this. And also, if you have a model with a high number of variables, sometimes this can be correlated. For example, income is highly correlated with education, right? Especially if you are at university, we were told that the more you stay in the university, the higher your salary. So if you have both education and income and status in your model, check that these variables are not correlated. So here I think everything is fine. All right. Now, this is also to, I'm going to tell you a little bit how to read and how to refine a model. Okay, so suppose that this was your model, right? Suppose that you have estimated this model and you say, well, in particular, it seems that everything is fine except that look at these 2 coefficients here. These 2 coefficients are household income specific to drive alone and shared ride. And actually, they don't look very different. So the test that I'm going to use, the log likelihood ratio test, in order to see if I can combine these 2 coefficients into one coefficient, because they look very similar. So maybe I can, there is not much difference I can combine. But I cannot just do this by looking at the values. I want to do this by in a statistically correct way. So I'm going to re-estimate the model by giving one coefficient to the household income, right? So I want to test if these 2 betas are equal or not, and I'm using the log likelihood ratio test the way you have seen in my last slide of the lecture, right? So you see that this model has a log likelihood of a final log likelihood of minus 820.4, and I needed to compare this with this, right? So by estimating one more coefficient for income, I'm just decreasing a little bit this value of 0.1. So 0.1 multiplied it by 2 is 0.2. And so my intuition was right. It means that I cannot reject the null hypothesis that these two coefficients are equal. So instead of using this, my log likelihood ratio test is telling me that I'm better to go with just one coefficient. So instead of using this, I will go back to this, right? So I will keep this model, right? So this is how to use the statistics in order to select the good model that I'm going to use at the end. So I want kind of parsimonious model. I want the model with the good variables. And I can do this with by using the log likelihood ratio test. Okay. So I can improve again my model by ease back to TI. But I can add more variables, number of workers in the household, and these are again specific to the driver and share ride. This is not significant. Probably I can get rid of this, or I can have the same variable for both drive alone and shared ride. Another way to kind of test another model is to have travel time and travel time specific to the alternative, right? So here, instead of having just one travel time, I have travel time specific to drive alone, to shared ride, and transit. The problem is that they are all negative, but I'm not doing very well with respect to significance. So it's very likely that these two are not much different from 0. So probably if I do the log likelihood ratio test, that will tell me to go back to one coefficient for travel time. But it's good to try, because if you have travel time specific to the alternative, you can have a value of time for each of the alternative calculated. So it's worth to try, although in this case, it's very difficult that we get significant results. This is mode choice without socioeconomic variables, because perhaps I want to apply the log likelihood ratio test in order to see if how much the socioeconomic variables are adding to the behavioral inside of this model. So how much level of service variable are explaining in terms of log likelihood, and how much socio-demographic variables are explaining, right? Okay, this is another example in which I have a piecewise linear travel time variable. So instead of having one travel time, I'm estimating a different travel time for a different duration. So I have a different coefficient for different duration. What does it mean? It means that if this is travel time, so if usually I estimate one travel time, right? This is one beta. This is the beta that I have in my first trial. But here I'm saying maybe depending on the duration of the trip, I have different travel time. So I'm saying I have one coefficient up to here. Then I have one coefficient here. This is 50. And then I have 80. So what I have here is that I have a very low coefficient here, right? Up to 20 minutes. You see, this is very low. Then I have a bigger one. Then I have a low one again. And then I have another big one here. Okay? So I have a piecewise linear relationship for travel time. And this is telling me that up to 20 minutes, my perception of travel time is negative, but not that high. Then between 20 and 50 is very high, and so on. And so this is significant and this is significant. Maybe this is suggesting me that the cut at 50 is the only one that is very significant. So instead of cutting this in 4 parts, I can cut this in 2 parts, up to 50 minutes and greater than 50 minutes. Again, this is nice, and this is done especially for destination choice model when you have distance. And you know, destination choice model is very sensible to distance. So short distance, the sensibility to short distance is very different from sensibility to long distance. So I've seen this many times done for destination choice model in which distance is piecewise linear relationship. The problem with that, yes?
Do they have any reference about how they categorize this?
No, this is just trial. The problem is this, it's that you can have many of these cutting points, and you need to try them, and the way you select is always based on the log likelihood ratio test. Although, you know, there are many, you know, we say that commuting time is usually less than 30 minutes. So 30 minutes is a good cutting point. So you can say from 0 to 30 minutes, from 30 to 60, and greater than 60. Here is clearly 0, 50, and 50 up. So once you have estimated a couple of these, then you have a sense of what's going on. Okay, so this is piecewise linear travel time. This is old-fashioned, and this is a squared round-trip travel time, something like this. You will get something like this. But again, if I remember well, see the log likelihood here, and compare with the linear, which was 820.3. So by including this squared travel time, you are not doing any better than the linear one. So I think that's what happens with the time. So we realized that by having this squared parameters did not improve much. That's why we use linear utility function.
So can I incorporate both linear and squared?
There will be a lot of correlation. So it's you can do it, but there are not many chances that you will get.
According to my experience, they will also find there were different signs. One got positive.
Yeah, and this is the correlation effect. Yeah. Well, this is constrained value of time. So you are telling the model. So you are kind of telling the model that the ratio of these two is a given value. So actually, I don't like this, not even in mixed logit. So it means that you are telling the model, in reality, you are telling the model that, for example, the ratio, you know that the average value of time in the United States is, say, $15 per hour, right? So what you do is that you estimate time, for example, and you constrain the cost in order to be the value of time divided by the coefficient of time. So you constrain one of these two. At the end, you just estimate one coefficient. I don't like this. And they do this when they cannot find a suitable value for the value of time. So something that when goes really wrong, for example, the value of time is too low or too high. So what I've seen, especially in practice, it's that they fix the value of time they want, and they estimate one of the coefficients, for example, travel time. I strongly suggest not to do this in research paper because it will raise a lot of trouble. They will say, you know, your data set is wrong, your model is wrong, and so on. What people are doing in mixed logit, I've seen this also from many professors, even the good one, I cannot tell you the names, but I've seen this many times from this guy. You know, in mixed logit, you say that, for example, the beta is a normal that depends on the mean and on the standard deviation, right? So you estimate both the mean and the standard deviation of this distribution. That's what you do normally in mixed logit. Now, sometimes you get very high value of the standard deviation, and so this will mess up your distribution. That's what they do, is they fix the standard deviation. I don't like this, because if the standard deviation is very high, it means that something is going on in your model. So better to discover maybe outliers, maybe wrong data, but it's better to let the model tell you which are this instead of fixing stuff. So you fix stuff in the practice because you need to have a model that is responding well to your policy. But especially in research, discover what's going on in your data set before fixing. Try to solve in an easy way either the value of time or the standard deviation of your distribution. So I do not recommend this. And I think that's all I have for today. Maybe there are 5 minutes maybe for question, or you can give me suggestion about what to do in the next few days, or yeah, questions.
Thank you. And do you suggest to delete the insignificant variables?
Okay.
The model, or we just keep using
the answer is it depends. It depends because, for example, in this case, right, you have out-of-vehicle travel distance, out-of-vehicle time, and these are specific to transit and share and drive alone and shared ride, and this is transit. Now, if it's something like this, what I will do is to combine them. I have one out-of-vehicle travel time, right? Because this will give you a significant coefficient with the right sign. So I will keep them. I will combine them. Now, for example, here the same. I think I will combine them. Now, there are, usually we delete the insignificant variables except when we think that is an important policy variables. And well, although the interpretation can be different in the sense that we say, well, this variable is not significant, or we can say maybe we don't have enough observation to estimate correctly that variable. So if you can combine, yes, if it's something that is not relevant for your policy, delete it. If it is important, relevant for your policy analysis, keep it and explain why maybe it's not significant. Maybe because we don't have enough information, maybe because you think that really it's not affecting the behavior.
If there's nothing to say about it here, but it is.
Yeah, just delete it because it will raise, especially in a paper, it will raise questions from the reviewers.
How about a constant?
The constant, I always suggest to have a complete set of alternative specific constant, especially because if you have a complete set of alternative specific constant, you are sure that you can reproduce your market share in the logit for the property of logit. So alternative specific constant, always the complete set, even if they are not significant. Other questions?
Did you suggest to use some mean center technique to avoid correlation problems?
I've never used that. So
yeah,
what?
So why in choice models only a few studies use mean-centered variable? Mean-centered variable.
What do you mean centered variable?
Like to subtract means from the values.
Ah. I never do that.
Why not?
Why not?
Yeah, because it can enhance the computation efficiency, or to avoid the correlation problems. If you want to include both variables, which you think they are important.
It's not the way I've learned discrete choice models. I needed to think about it, but I never do that. I just use the data the way they are in the database. I usually don't manipulate. Well, the way I estimate, I don't like to manipulate a lot my data. I like to have the data set and estimate my model from the data I have. I don't like this manipulation. I think they are artificial. I prefer to clean the data instead of trying to clean the data the way I want. I like the data to tell me the behavior of the choices. I don't like to manipulate the data too much, but I've never done this, so I don't have experience on that. As I said, this was a big overview of what is the classical discrete choice models and why we want advanced stuff. So the next 4 days are going to be the advanced discrete choice models, right? The true ones. Okay. I'll see you all tomorrow. Thank you.